we can compute the mechanical power delivered by the pulling force, which you might remember or might not, but the power delivered by something is the force times the velocity at which the thing is moving. And we know what the force was, which was VL squared B squared over R, and we multiply by V, and we get V squared L squared B squared over R, which actually is suggestive, and we'll see that in a second. We could also compute separately the power dissipated in the rod, because we know the power is I squared R. So we know the current was VLB over R quantity squared, right? VLB over R, and we square it. This R here cancels one of the R squares there, and we get V squared L squared B squared over R. And of course they are the same, because all of the power that's being lost by the thing, that all the energy being lost by whoever's pulling it, is being gained by the circuit, or and then being dissipated as heat in the circuit. This was actually kind of suggestive, because if we go back here and we just naturally group this, we'd say VLB squared over R, which of course was E squared, or EMF squared over R, which is a different form for electrical power. So we're not surprised really by that, but it's worth seeing. All right, a device that converts mechanical energy to electrical energy is called a generator, or sometimes an electrical generator if you need to be clear about it. Our rod and field is a generator, but it's not a particularly good one. All right, you've got to basically keep the thing moving at constant speed over a long way. You could imagine taking like that, what we saw there, where you had a magnet dropped on a coil, like we saw in the last thing, but it's still kind of awkward, and of course at some point you're going to run out of room, and you got to reset it, and that's annoying. More practical generators use a rotating coil. So we have a thing here, it's spinning through this magnetic field, so the field threading through the coil is changing all the time because the orientation is changing, which will generate an EMF, which generates current through the device. And then they've got these things called slip rings that allow this to turn on here and create a closed circuit, and so we can get the current out, and we can do stuff with it, put a resistor or whatever. So this is the more common thing that you would see, something like this. This is also very simplified, but much more common. Now the diagram might look a little familiar to you. It might not, but it might. It's nearly the same one we had for an electric motor. There we were turning electrical energy into mechanical energy. And in fact, every motor is a generator and vice versa, although that might be more efficient at one role than the other role. So here we had the idea that if we feed a current through the coil, it will spin in a magnetic field. So we're able to make this axis spin just by pumping current through. Instead here, if we can somehow drive this loop, we can pull out current and then go back and forth that way. So we'll see that a lot. On the other hand, the rotation of the loop does make things a little bit more complicated. The EMF is varying sinusoidally. It reverses direction twice a cycle. It looks something, in fact, like this. This generator is called alternating current, or AC. Commercial and residential electricity is mostly AC, which was pioneered by Thomas Edison. He was locked in a war, a commercial war in the late 1800s with Nikola Tesla, who was pushing a DC power generation system. Edison won out, partly because of efficiencies in the work, and partly because Edison was a very ruthless competitor, and Tesla had less killer instincts and a little bit less luck. So there's still people who talk about Tesla, and it's still, the Tesla DC generation system is still of interest, but is not been commercially successful in the same way. All right, here we have a square conductor moving through a uniform magnetic field directed out of the page. Which of the figures shows the correct charge distribution on the conductor as it moves? So let's set up a coordinate frame. And what we have here is the velocity is moving this way, and the magnetic field is pointing out of the page like that. So we see that the force that comes out would be perpendicular to both of them that way. So positive charges would feel a force that way and move to the left, and negative charges would feel a force the other way and move to the other sense. So that turns out to be pretty clearly E as our answer.